Hello there, welcome back to our channel, and we continue our discussion with the differential amplifier. As you can see on the schematic, let's say we have been given a design problem to design an amplifier for a gain of 20. So we want to have amplification with the gain about 20. So for example, if I apply an input signal V in that is equal to 10 millivolt, and the output would be gain multiplied by the input, and if the gain is 20 and V input is 10 millivolt, so 20 into 10 millivolt, I would require a gain of the output would be about 200 millivolts. Okay. And so based on this assumption, we can actually see that the ratio of output divided by the ratio of input is equal to 20. And here the output is VID, that is the difference between the two inputs, that is V1 minus V2, and I want it to be 20. Now let us design it for that purpose. So I will apply a sinusoidal signal to the input of the amplifier that needs to be amplified. And these will be two same magnitude signals with let's say 10 millivolt peak. And it is a positive going at the base of the transistor Q1, and at the same time it is negative going at the base of the transistor Q2, and the peak value of this signal, it's let's say 10 millivolt, and here it would be minus 10 millivolts. So total 20 millivolt peak to peak signal I have to apply. Now I am given a supply voltage is plus minus 5 volts. So I have a power supply with dual voltages, that is V plus applied to these two nets, and the V minus is applied right over here. Okay, and now I am using the 5 volt and minus 5 volt, which is connected as shown over here. And the first task is to calculate, based on the equations and the formulae, we want to calculate and determine the bias points, the bias point of the circuit, because this is also called as DC operating point. Okay, so it is about calculating the currents and the voltages that will flow into the circuit. Now we see that this is a perfectly symmetric circuit where I am using the two identical transistors Q1 and Q2, and these transistors are 2N2222. They are, if you Google them, they are general purpose small signal amplifier transistors. So we want to use them for the amplification purpose. And I am using the two resistors for the collector. One end of them is connected to the collector pin of the transistors, and the second end of these resistors are connected to the positive voltage supply. Then the emitter pins of these two transistors are shorted together, as you can see right here. And from the common point, and in between the common point and the negative minus 5 volts, I am connecting the resistor RE for this circuit. Now the values that you see for the resistors chosen are temporary, because we are going to change them and we have to use the values based on our calculations. So let us do that one by one. So our gain requirement is 20, and let's say the bias current IC is given as 1 milliampere. So the collector current that will flow through these transistor circuits, so here is that current which is called as IC1, and here is that current which is called as IC2, and IC1 is equal to IC2 is equal to IC. We will make sure that since the circuit is symmetric in both the branches, same current flows via the transistor. So here is that currents IC1 and IC2 coming, and then you have the base currents also, let's call it IB1. Here you have another current, let's call it IB2. And then you have the third component of the BJT currents, that is IE2, and here your current is IE1. And the current that comes out here is IE, which is the sum of IE1 plus IE2. Now, if we assume the transistor collector current is 1 milliampere and the beta of the transistors is about 200. So let me show you if we can actually have the beta value known. So either I will go to Google the data sheet of the transistor, or the other way I'm using the circuit simulator. So what I'll do, I'll right click this transistor model and I will click here the pick new transistor option. But before that, I would like to show you, we are using this transistor from the manufacturer as name suggests. It is a NPN transistor, and these are the maximum voltage and the currents ratings. So specifications are you can have maximum 30 volts across the collector and emitter of these transistors, that is VCEO. O stands for open circuit voltage, and you have the collector current is about 800 milliampere the transistor can withstand. Now I will click pick new transistor, which opens the spice model. Here I see well, I can see that I'm using the very first row of the transistor, and these are the two voltages and currents respectively. Then model, dot model, that's the spice line. 2N2222, it is NPN. IS stands for reverse saturation current through the PN junction diode, or it is also called as scale current, which is about uh, 10 femtoamps. Then VAF, that's I think that's an early voltage or something like that, but we want to just we don't want to get into details of that. We are interested in this beta factor, which is 200. Okay, and the turn on voltage and other factors are also given for this transistor. So we are just using the beta value here. You can go for the other things here. Click OK. So now we have this beta that is equal to 200. Having said that, once we know the value of beta, it is relatively easy to theoretically determine the value of your base current, that is IC divided by beta, and that comes out to be 1 milliampere divided by 200. That is your beta value, and that comes out to be, let me calculate that. So it comes out to be 5 microampere approximately. Okay, 5 microampere. And finally, you have like IE1, or we will say simply IE, that is the sum of IB plus IC. So you see 5 microampere in comparison to 1 milliampere, it's pretty small. So you can approximate IE to be approximated equal to IC. And that is also your emitter currents. Now we know that this part, actually I1 and I2, they are the emitter currents of the two transistor. And here the I is the current flowing through this resistor, which is the sum of these two components, right? So you would have to say here I2 here, and let me call it I1 here, okay? And I1 is approximately equal to I2 is equal to I1 is approximately equal to IC, whatever these are current, and IC here, I would say is equal to IC1 is equal to IC2. Okay, and now the value of IE would be I1 plus I2, and it would be about approximately 1 milliampere plus 1 milliampere, approximately 2 milliampere. Okay, so this current that is flowing is approximately 2 milliampere that we have, and the collector current here is 1 milliampere in each branch of the transistors. Now, I have, let's say, the V plus, that is 5 volt coming over here. I have 5 volt coming over here, and I would like to have the DC bias level at the outputs. So remember, when I'm doing the analysis for the one branch of the circuit, for example, left or right, so it is applicable to the another branch because the circuit is symmetric. Okay, so let's focus on the left side. That is, we are doing the analysis for Q1, which is relevant with the analysis and applicable to the analysis with the Q2. So here the voltage at VO1, which is at the collector pin of the transistor, I want the DC bias level is about 0 volt approximately. Why I'm choosing 0? Because my output signal swing will start from the DC bias level of 0 volt, and it can go high up to 5 volt DC, which is the maximum power voltage supply in the circuit, and negative, the down, it can go to minus 5 volt right over here. So that is what I expect for this branch of the circuit also. Okay, so let us say I assume here is my 0 volt, right? And now I can actually get the values of the RC. RC would be in that case 5 minus 0 divided by 1 milliampere. So it comes out to be 5 divided by 1 milliampere, 5 volt divided by 1 milliampere, and it comes out to be 5 kilo ohm. Okay, so let us pick up those values and replace that. So let's say I'm using the resistor values to be 5 kilo ohm because we want the gain of 20, and we have used the collector current about this one. So let's say 5 kilo ohm each. So I choose here. So all set. So now what we want, the second condition of your transistor, that you want the Q1 and Q2 to be operated always into the linear or active mode. So that means your transistor characteristics would be such that you have, let's say, the output characteristics about this like this. You have IC max here, and you have VCE max here, and you have, let's say, this is a kind of curve you will generate for given VBE, and then you want your transistor to be operating right to this line, which is your linear or active region, and this region is your saturation region of the transistor. Okay, and then somewhere here you will say, I have a bias point of the transistor. For example, you choose this value of the current and voltages. So here is your VCE, and this is the value of your IC. Okay, and IC max is here from the data sheet or the SPICE model is about 0.8 ampere, and VC max is about, we've seen that that is about 30 volt. So you are much less in that value. So you want to make sure that you operate at this bias point. So you need to get the values of the correct current. So here you are saying I have a value of 1 milliampere for the current, and now you want to determine the what is the voltage across the collector to emitter of this transistor. So what I see here from this analysis, now I have a collector pin biased at 0 volt, and I have this transistor is my NPN transistor. So let us focus here also. This is your NPN transistor, and that's your pin, collector pin, that's your base pin, and that's your emitter pin of the transistor. Okay. So what I will do is, I know that in order to bias the transistors in the linear or active mode, the base emitter junction should be forward bias. So here is, I have one diode that is a forward bias, that should be forward bias, and the collector base junction should be reverse bias. So I have another diode right here. So in order for this diode to be forward bias, I want the VBE, that is the applied voltage, approximately 0.7 volt. That is what I want. So VBE is approximately 0.7 volts. So let me write here. This is my VBE, approximately 0.7 volts right here. And now here I have 0 volts at the collector pin of the transistor. It means my voltage at the collector pin VC should be greater than VBE, that is more than 0.7 volts. So here at the base, I have the VB1 or VB here, that is about, let's say, minus 0.7 volt minimum. I should have. Maximum it can go negatively, minus 0.8, minus 0.9, and so on. So I would fix this voltage to be, let's say, minus 0.8 volt, for example, at both the. So that is my DC bias level. See how I'm setting the voltages right here. So what I'm going to do here, I will right click and let us set it to DC bias level about 0.8, or I have to choose the DC voltage source initially. So DC value is 0.8 volts, and let me move it closer to the voltage source. That's much better. Similarly here, I would click and select the DC value of 0.8 volt. I had used the sinusoidal source in the previous analysis. That's why I want to do some changes right here. So now your circuit looks like all being set. So 0.8 volt is the DC level for the base voltages we have set. Now this diode is forward bias or reverse bias. We have to check once again. So let's clear this out. For example, correct, and we'll see that this is my diode, and here is 0 volt, and here is minus 0.8. So P is at negative voltages and N is at the 0. So obviously this diode is reverse biased, and this diode, how much we want, it is minus 0.8 volt at the positive, at the P type material, and at the N type material we would like to have at least I want to make it positive, right? So I would like to apply more negative voltages right here, and the difference should be about 0.7 volt right here. So if I apply minus 1.15, because that's minus 1.5 actually. Let me check here. Right. So I have, let's say, minus 0.8 at the P, and at the N, I would, let's say, minus 1.5 volts right here, which is the voltage right here, minus 1.5 volt. So the difference between these two is about 0.7 volt, right? That's good. So we are all set, right? That makes sense. So minus 1.5 is here, and here is minus 5 volt. So, and the current IE, we have calculated 2 milliampere. So what is the value of RE? RE would be VRE, which is basically VE, this voltage. We have labeled the net, okay, divided by value of the current, that is IE, and it would be voltage difference well, it's not VRE. It would be VRE or VE minus V minus, actually. This is the voltage drop because that's the voltage difference between the 2 points. And that is about minus 1.5 minus of minus 5 volt, which is the negative voltage source divided by 2 milliampere. And that comes out to be minus 1.5 plus 5, which is about 3.5, 3.5 divided by 2 milliampere. And that comes out to be, let's calculate that. It comes out to be approximately 1.75 kilo ohms. So let's do that. Let us change the value right here. So we are progressing step by step to select the values of our resistors. So we have for a given transistor here. So it is about 1.75K, right? So it's about 1750 ohms. Now, so we are expecting that with such DC biasing levels and calculations, we will approach our our transistors circuit differential amplifier always be in active regions, and we'll have a linear amplification of the applied signal. Now, on this DC voltage levels, actually, which is the 0.8 at the inputs. So let me draw it here. So you have this 0 volts for the input signals, and let's say somewhere here you have my 0.8 actually. Is that well, I made a mistake here. Actually, we have used the 0.8 here and we assume the minus 0.8 here. So there is a mistake here. So let us correct that again. Okay, so we have assumed this 0.8 right here. Let me just correct that. Okay, yeah, so 0.8 here. And then this is plus 0.8 then now. And plus 0.8 plus 0.7 would be 1.5 plus 1.5 is the voltage at here. So if it is plus 1.5, we want it will be plus 1.5, and this will be plus 1.5 plus 5. So it would be 6.5 actually. So it would be 6.5. Let me correct that. So you have to be accurate in calculation. So that is your 6.5 volts divided by 2 milliampere, and accordingly the resistor value is going to be changed. So let's calculate that. So it is 3250. That is 3.25 kilo ohm. So because the voltage got increased, so your resistor got increased for a given value of current. So let's put up that value here, 3.25K, 25K, and that's it. So we have done such adjustment. I'm coming back to our discussion now. My input signal swing would be like this. I have 0 volt, but my DC bias level is about, let's say, it's pretty close to 0. It is about, not here, not here. It would be like this. It is 0.8 right here. That is my DC level. And then on that DC level, I am writing an applied signal about whatever value I want to. So I have chosen about 10 millivolts, for example. Accordingly, it will go up, okay, and down. Similarly, this will happen for this section of the transistors. So with the voltage values checked and all that, we are set to run the first analysis. let us apply some equations and see if those how those values correspond to. So what we see, the output voltage of the transistor 1, that is Q1, by formula is given as GM. I'm using it for one branch, so it is applicable to another branch also. So I would not specifically write it for VO1 and VO2. Rather, I would say I am writing it for one branch, so it is applicable to another branch. So I will say output voltage would be GM times RC, that is your gain. Here is your gain, and multiplied by V in. Okay. And GM value is the DC value of the collector current divided by thermal voltage VT. Here VT is KT by Q, which is approximately 25 millivolts at 27 degrees centigrade, that is at the room temperature. So we have chosen the value of IC to be 1 milliamp divided by 25 millivolts. That comes out to be, let us write this value here, 1 milliamp divided by 25 millivolts. So that is just 1 by 25. And it is 0.04 amps per volt. That is your transconductance. Once you have the value of your transconductance, VO would be 0.04 multiplied by the value of RC we have chosen, 5 kilo. That is 5K. And the input voltage is what we apply to it. Let's say 10 millivolts. That's we want, for example. So let's calculate or even the 1 millivolt or something. So let's calculate that value. So how much is the output? Let's do that. So it comes out to be around 2 volts. So we have a gain of about 200, which is your GM times RC. Okay. So that is how you get this analysis done. So with all set, we have a signal that we will apply here. We'll have the output 200 times larger than the input signal. And initially we had predicted we want a gain of only 20, but now through the values we have chosen, we have a gain of about 200, right? So let us try to do that. How we can do. First thing I would like to do, run the DC analysis, which is .op command, which is right over here. And what I'll do, I will just disable all other analysis. For example, transient, I don't want for a moment. So I will just disable it with this command. And now with that said, I am all set to run this. So let us check our table that is given by the circuit simulator. One by one, we will do all this, demystify all these voltages and currents. So output voltage level is now VO1. Let me calculate here, 1 volts. And we have theoretically calculated it about 0 volt. We wanted it to at about 0 volt. So now if we go for this results, and we'll apply the transient signal on top of the DC bias voltages at the base pins, our output signal will ride up and down from this DC bias level, that is 1 volt. Okay, that's fine. Now the VB1 is what we have said, 0.8 volt, and voltage at the emitter is 0.15. So this is what we predicted. We wanted it to be 1.5 volt, and this is 0.15 voltage. But let us see if our PN junction diode at the base emitter junction is forward bias or not. So that is possible by taking the subtraction between these two, by analyzing the voltage difference between base and emitter pins. So base is at 0.8 minus VE is 0.15. So it is about 0.7 something. So that's our that shows it is forward bias because it is greater than the difference is greater than 0.7 volt. Now you have like plus minus 5 volts for our supply. VO2 obviously symmetry is working here, and then VB2 is also there. Now look at this value of the collector current. We calculated it about 1 milliampere and it is about 0.7 milliampere. So there is a difference between 0.3. So we can adjust the value of the collector resistors to again set back to the alter the value of the collector currents. The base current we predicted 5 microampere right here, you see right here, but now we have about approximately 4 microampere, so it is pretty close. Then I of Q1 will be, of course, IC plus IB. It is about 7.7 milliamp again, or simply zero point 0.8 milliampere approximately. Again, IC2, IB2, and IE2 will be just what we have it for transistor 1. Again, then this is the resistor current RC1 that is flowing right here. We go a little bit up, and the current through the RE, this one, we said it will be 2 milliampere theory, and it is now 1.5 milliampere. So it's close. There is not drastic change. So it is matching. So you need to just tune in the values of the resistor in order to match with our theory results that we calculated. And then other things are your current through the resistor R2, current through the voltage source V1, current through the voltage source V2, and so on. So I think it's pretty decent. Now, the theoretical gain we have calculated is about 200, and we design it for 20 actually, and we'll now simulate and we'll see how much gain we have. Okay, so answer is here. I have again printed the operating point. So I forgot to check the biasing condition of this diode that is between base and the collector. Remember, base pin is the positive and the voltage here is 0.8 volts, and the voltage at the collector pin is 1.05. The voltage difference is just 0.2 volt positive. We want it to be negative. Collector should be at least 0.7 volts larger than the voltage at the base. So if I have like I have to adjust the level of the base here, for example, right? So if it is 1 volt here, I need to adjust the base to be, let's say, 0. For example, if I set it to 0, that would be better. So let me set that 0. Here it is 0, and here will also be 0. And with that, I will check the operating points again. Let us click that. Now you can see I have this diode, and the collector voltage has changed a level to 1.66, and the base voltage is 0. So obviously N is at the positive, the P is at the 0. So this diode is the diode here is reverse bias. What about this diode? It is 0, and now voltage should be more than minus 0.7. So VE is minus 0.64 actually. Pretty close to what we want, but still I'm suspecting that whether this diode is forward biased or not. But let's check if we have the current. So current collector current is 0.6 milliampere. Base current is 3.2 microampere. It makes sense. And the current through the resistor RE is about 1.3 milliampere. Yeah, so we can now do that, try that. Now, what I have done to verify our calculations and the theory predictions, I have chosen now the sinusoidal source. Right click here, let me show you the values that I have used. It's a sine wave source. So DC offset is 0, which is also providing a bias to the base pin of the transistors. Then I'm using 10 millivolt peak, and then I'm using 1 kilohertz frequency signal. Number of cycles are 10. Same I'm doing it for the transistor Q2 right here, the same source with the same value. So I'm using the differential signals. One is going from positive to negative at Q1, and for Q2, this signal is going from negative to positive. Okay, and the well, if I apply the signal at the Q1, output will be inverted at VO1, and the signal at Q2's base, again, the VO2 will be inverted, right? And for the signal applied to Q1, if I take the output from VO2, signal will be in phase, output and inputs will be in phase. Same here, I apply the signal at Q2, and the signal here at the VO1 will be in phase. Okay, so in fact I have to apply here -10 actually, because it should be oppositely varying signal. So it is -10 millivolt, because you see this is positive going signal, this is negative going signal. Then only I will be able to plot the difference for that gain, the combined gain of these transistors, right? What would be the combined gain theoretically? Let's calculate. For example, here VO1 would be GM1 times RC1 times V in 1, which is this V in 1, and VO2 will be GM2 times RC2 times V in 2, and the VO out, that is final output, is VO1 minus VO2, which is, let's say, GM1 RC1 into V in 1 minus GM RC2 into V in 2. So it would be GM times RC, assuming the GMs are same, resistors are same, VID, where VID is V in 1 minus V in 2. So that's it. So it is, the gain is GM times RC, which is what we predicted. GMs times RC is about 200. So we'll see, whatever the signal we are applying, do we get the gain output signal 200 times larger than the input signal? So let us click, I have enabled the transient analysis. Let us click the sinusoidal, let us click the run simulation, and boom, we are. So now let me get rid of the drawings. Just remember, we have the gain of GM times RC, which is 200. Clear all drawings. Here I'm plotting the signal VB2, which is this signal at the base. I also want to plot VB1. So let me click here, and then I go to schematic. The DC bias here is 0 volt here. So now you see VB1 and VB2 are two 10 millivolt peak signals opposite in phase. One is going positive to negative, another is going negative to positive. Good. So that's one. Then I have VO2 and VO1. VO1 is a blue. VO1 is the output. The DC bias level is here 1.38 volts. And from that, I have the swing, negative swing. So you see, VB1 is the pink line in the top graph, and in opposite phase, I have this VO1. So how much is the amplification, that I will just tell you in a moment. Okay, the combined gain is GM time RC. Remember that. Now VB2 is the green signal that is going from negative to positive, and VO2 is the red signal, again out of phase. Okay, and if I take VB1 and VO2 as input and output respectively, they are in phase. So the pink line and the red line, the red color curve. Similarly, the green trace and the blue trace are the input and output. You just see it yourself. Now I want to have the voltage difference, that is VO1 minus VO2. So it is obviously the DC bias is starting from 0, what we actually predicted. Uh, why it is 0? Because the individual DC biasing level, look at the very down left, your the circuit simulator is highlighting the DC operating point. It is 1.38 volt, and VO1 all VO2 also 1.38. So the combined DC bias point is VO1 minus VO2, which is 0. So it's a very nice swing we are getting, and it is going up to negative about, let's say, about 2.5. Okay, so obviously is it 2.5? Yeah, 2.5. So it's about 250 times, output is 250 times the input applied signal. Okay, so you have a 10 millivolt signal, you have 2.5 volt amplified output. So that is how you successfully design this amplifier for a gain of 200. Just tweak in with your values about resistors and transistors, and play with around. So you have successfully done this analysis. If you turn off the second signal, for example, let's say I want to keep it 0, that's it, there is no signal, and then run the analysis again, and you will now see the output is only printed for this one, your VO1 VO2 outputs, and the output voltage level is about, maximum is about 1.1 volt, right? So half, the gain is half now. So that's it. So this is how you can actually design your stuff. Just I encourage you to play with it for your convenience. Hope you like this video. We'll do the AC analysis and the body plot sometime later.